music. In the name of Allah, the most gracious, the most merciful. Praise be to Allah, and peace and blessings be upon the Messenger of Allah, our Master Muhammad, and upon his family and all his companions. To continue, in the previous episode, we provided a general idea about communication methods between stations using communication links, and we explained 3 of those methods. The first method is using power line carrier, the second method is using pilot cables, and the third method is using radio channels, also known as microwave channels. In this episode, we will move on to the fourth method for transmitting signals to power stations, which is currently in use and the most widespread. It is definitely the most expensive method for signal transmission, which is using fiber optic cables. So stay with us. Cables. So stay with us. Nations Renaissance. We usually use method for lines that are up to 100 kilometers long, where signals are transmitted at extremely high speeds in both sending and receiving, approaching the speed of light in a vacuum. They are transmitted in the form of light signals, not electrical signals, and they travel in the form of light pulses. The first link was installed in 1977. All data transmission methods, including this one, use it at different frequencies. Light is part of it, within a higher frequency range than electrical frequencies in copper wires. Electromagnetic interference is higher for data in copper wires like Ethernet cables than fiber optics. Fiber optic cables made of glass or plastic are insulators, not allowing electric current and unaffected by electromagnetic field. Electrical supervision frequencies transmitted through copper wires. Electromagnetic interference is more likely in data transmitted through copper wires like Ethernet cables than in fiber optic cables. Fiber optic cables made of glass or plastic are insulators and immune to electromagnetic fields, preventing interference and ensuring signal quality. This resolves issues like weak signals or data obstruction. Fiber optic cables used for short distances between power stations are unmatched by copper cables for distances not requiring signal amplification. However, interference can still occur with fiber optic cables. Fiber optic cables prevent interference, improving signal quality and resolving issues like weak signals. Used for short distances in power stations, they outperform copper cables over distances not needing amplification. Interference can occur if cables are closer than 1/10 of the wavelength. Wavelength is speed divided by frequency, so allowed distance decreases as frequency increases. There are 2 types of fiber optic cables. These properties are what make fiber optic cables unmatched by any copper cables over distances that do not require signal amplification or boosting. But can we conclude from the above that interference can never occur when using fiber optic cables? We cannot say that at all. So, if the distance between these cables is less than 1/10 of the wavelength, then interference can occur between the fiber cables. Here, the wavelength is equal to the speed divided by the frequency, which means that the allowed distance between the cables to avoid data interference decreases as the frequency increases. Fiber optic cables come in 2 types, either single-mode fiber optic cable or multi-mode fiber optic cable. Single-mode fiber, or what may be called monomode fiber, is used for direct connections from the transmitter to the receiver in applications that require high speed and long distance. The interference This signal is very minimal, and the wavelength of the signal transmitted through it reaches 1300 nanometers using fiber up to a distance of 60 kilometers, and it reaches 1550 nanometers using fiber up to a distance of 200 kilometers. This type of fiber optic is characterized by a small core radius, which reaches 9 micrometers, where micro here means 10 to the power of 6. On the other hand, multimode fiber is cheaper than the first type and is used when accuracy is not critical or important. It is used in technologies that do not require long distances, meaning less than 1 kilometer, and of course the signal will experience distortion if the distance exceeds that, which means we will need to use a repeater unit or a signal booster. Therefore, it is preferable to use this type of fiber optics in internal computer networks. Light travels refracted along cladding. In single mode, light travels directly. In multi-mode, it reflects internally. Core radius is 62.5 Wavelength of multi-mode fiber optic signal can reach 820 nanometers. Max distance is 3.5 kilometers. Max distance for fiber optic is 100 kilometers. Solutions for long distances use OTN and SDH protocols. The maximum distance for fiber optics is 100 kilometers. For distances over 100 kilometers, solutions include using OTN and SDH protocols. Wavelength division multiplexing (WDM) technology is chosen based on data, nature, size, and distance, considering budget. SDH protocol with STM1 or STM4 rates and boosters or repeaters can amplify signals effectively for electrical systems. For high data rates, WDM with ADFE or Raman amplifiers is used. Though costly, it allows direct transmission up to 300 km with minimal issues. Using the SDH protocol at a data transfer rate of STM1 or STM4, along with using boosters or repeaters at the midpoint or any estimated distance where the signal may need amplifying, is usually effective for electrical systems or any system that requires the transmission of cascading signals. If the connection is for a system that requires a high data transfer rate, you can use wavelength division multiplexing (WDM) technology along with an ADFE amplifier or a Raman amplifier. However, this solution is more expensive, but it ensures direct transmission over distances of up to 300 kilometers with a high data transfer rate and minimal issues. You can access this link to learn more about the differences between the ADFA amplifier and the Raman amplifier. There is a simulation program from OptiWave where you can experiment with these scenarios and study them before making a choice. Huawei suffers in providing such solutions. This topic is general knowledge, not for electrical engineers. For communication engineers, fiber optic cables are described by core count. A 2-core fiber has 2 fibers, a 12-core has 12. Core counts can be 2, 4, 6, 8, 10, or 12. Modern systems use 1 fiber for data. In the trunk and optical fiber, usually, fiber optic cables are described by the number of cores or fibers inside them. For example, if this fiber optic has 2 fibers, we say it is a 2-core fiber optic. If this cable has 12 fibers, we refer to it as a 12-core fiber optic. The number of fibers or cores inside the fiber optic can be 2, 4, 6, 8, 10, or 12. In modern systems, all data is transmitted and received using just 1 fiber. And don't forget, before purchasing the required fiber optic, make sure to check the fiber optic connector and that it is compatible with the relay's communication port, as it varies from one relay to another. There are many types of fiber optic connectors, including ST, FC, SC, LC, and others. You can find out the required type by searching in the relay manual under the keywords communication or optic connector. This image illustrates the differences between each type. Fiber optic cables can be connected between all relays at both ends of the transmission line by using 1 communication channel or by using 2 independent communication channels where each channel has a different and independent method from the other. The first method is to directly transmit fiber optic between both relays, known as a dedicated link, using single-mode fiber optic. The fiber optic cable runs from the local differential relay in the local substation to the remote differential relay in the remote end substation within the underground line located at the top of the transmission tower, which is called the OPGW cable. Alternatively, it can be extended or laid through a trench cable. Now, it is possible to manufacture connectors for both overhead lines and underground cables that have a fiber optic cable in the middle. The OPGW cable, also known as sky wires, located at the top of the tower, can be utilized for several reasons. First, it can be primarily designated for protection against lightning strikes and grounding them. Second, it can be used to transmit communication signals between the 2 stations through the fiber optic located in the middle. Third, when a ground fault occurs, the ground fault current will directly flow from the ground to the nearest grounding scheme of the towers carrying the wires. Then it rises through the tower to the underground line installed at the top of the towers, passing through it back to the station it originated from. At the last tower in the line, a grounding connector of this tower is directly connected to the ground of the station, where the ground fault current only flows in a closed path and must return to the source it came from. If there is no lightning protection on the tower, or if it is cut off, or if the overhead line is of medium quality, this means that the ground fault current will return through the ground. However, in many cases, the ground may have high resistance, and in this situation, the value of the fault current will be very low. This fault can be classified as an open circuit if the ground fault current cannot return to its source. In the case of underground cables, the ground fault current will return through the armored cables via the armor. If there is no armor, the ground fault current will return through the sheath. The ground fault current usually has 2 paths to return to its source. The first path is through the ground, and the second path is through the ground at the top of the tower. The current flows between them in inverse relation to the resistances, meaning that the lower resistance will carry the larger current. This image illustrates how the ground fault current flows when there is an OBGW at the top of the tower. This image illustrates how the ground fault current returns to its source in the absence of OBGW, where we see that the ground fault current only returns through the ground. So the first method for transmitting fiber optic between all relays at both ends of the transmission line is by using OBGW cables. The second method for transmitting fiber optic between the stations is not direct, but rather through a multiplexed link. Through this, all communication signals such as voice, CCTV, and telecontrol are transmitted, in addition to the required protection signaling. This means that connecting fiber optic between the relays is specifically designated for transmitting protection signals. The second method, which is the indirect method, uses a multiplexer and is used for general purposes. It is not specifically for transmitting protection signals. Rather, it can transmit telephone signals, CCTV, and others. There are several ways to transmit information to the other side using a multiplex link without any interference between them, depending on the type of signal being sent. If the information to be transmitted is an analog signal, a different frequency is used for each signal, which is called frequency division multiplexing, FDM. However, if the information to be transmitted is in the form of a digital signal, it won't have any frequency, so the concept of analog is used. Time division multiplexing, TBM, TDM. In this method, the signal is divided into several time slots, or channels, with each channel dedicated to transmitting a specific piece of information. Currently, in the stations, wavelength division multiplexing, WDM technology is being used. In the medium space, you can update about the medium space level. It is a technology that sends multiple signals over a single fiber using different wavelengths. This technology allows for the transmission and retrieval of information through a single fiber optic. In addition to multiplying capacity, the WDM method is associated with optical carrier, which is usually described by wavelength, while the FDM method is associated with radio carrier, which is typically described by frequency. According to this diagram, the fiber optic cable is extended from the required relay to the converter or the interface adapter, which may also be called the communication interface unit, to convert the optical signal into an electrical signal. The purpose of this converter is to create a separation or segregation between the different sections of the station. Therefore, it acts as a boundary between telecommunication engineering and power engineering. From the side of the relays to the converter itself, it falls under power, while everything after the converter falls under telecommunication, meaning communications. The purpose of this segregation is to precisely identify the location of the problem and to determine which specific section it pertains to so that there is no confusion between them. This interface adapter could be of the P591 type for the MICOM relays that have become JLM, or it could be of the G703 type for ABB relays or other types. We connect a fiber optic cable coming from the differential relay, which is of the multimode fiber optic type due to the short distance between them. Then, we output an Ethernet cable. It's important to note that there are several types of Ethernet cables, and it's crucial to choose the right Ethernet cable appropriately to avoid affecting the performance of the other components in the system. For example, if we have an interface unit with a data transfer speed of 100 megabits per second, and it is connected to it via a Cat5 cable, which has a maximum data transfer speed of 100 megabits per second, then we will not have any problems. The term cat is derived from category. If the interface unit's data transfer speed is 2 gigabits per second using a Cat5 Ethernet cable with a maximum speed of 100 megabits per second will slow the system. Cat6 Ethernet cable supporting up to 10 gigabits per second is suitable. The cable type determines the appropriate outlet, requiring a Cat6 socket for a Cat6 cable. This table shows differences in Ethernet cables regarding data transfer speed and maximum distance. Fiber optic cables offer speeds from 10 to 400 gigabits per second, depending on the receiving device. An Ethernet cable of type Cat6 requires a socket or outlet of type Cat6, and this is something basic with no discussion about it. In this table, we will see the difference between using different types of Ethernet cables in terms of the relationship between data transfer speed and the maximum distance the cable can be used. We want to point out here that the data transfer speeds of fiber optic cables range from 10 gigabits per second to 400 gigabits per second, depending on the receiving device and its nature. The era of the nation's Renaissance, a period of Assuming the interface unit has the right speed, we seek an Ethernet cable with matching speed. If initially slow, it can't process data quickly, causing traffic, overheating, and burnout. The adapter receives a fiber optic cable from the relay as an optical signal and outputs an Ethernet cable as an electrical signal. Ethernet cables from adapters feed into the PCM multiplexer. The unit is near the multiplexer with a max distance of 10 meters. Ethernet cables are for short distances, not exceeding 90 meters, ideal for LANs. Let's return to the topic. The interface adapter receives a fiber optic cable from the differential relay and outputs an Ethernet cable. We gather all Ethernet cables from the interface adapters and feed them into the PCM multiplexer. The interface unit is near the multiplexer. Ethernet cables are for short distances. The multiplexer takes multiple signals and outputs one. This concept is also in the protection relay, where numerical relays convert signals from the CT and VT into digital numbers. PCM stands for pulse code modulation. The interface unit is near the multiplexer. Ethernet cables are preferred for LANs. A multiplexer inputs multiple signals and outputs one. In protection relays, numerical relays convert analog signals from CT and VT into digital. One analog to digital converter can replace 6. The PCM multiplexer transmits to stations, receiving Ethernet input and outputting fiber optic from the protection relay. Communication interfaces bridge these connections. A multiplexer inputs multiple signals, analog or digital, and outputs one signal. Thus, it is a MISO device. In protection relays, multiplexers convert CT and VT analog signals to digital. PCM multiplexers transmit station information. It inputs Ethernet and outputs fiber optic. Communication interfaces bridge them. All station Ethernet cables input into the multiplexer, outputting one fiber optic cable with all station data. This allows one fiber optic cable for all station data instead of separate cables. So, we input Ethernet cables coming from communication interfaces into the multiplexer, and then we output from this multiplexer a single fiber optic cable that collects all the information. This way, it allows using one fiber optic cable for everything instead of using separate cables for each signal. We use a fiber optic cable, which is transmitted through the OBGW at the tower top. Use the network by using a standard multiplexer. So, we input all the Ethernet cables coming from multiple communication interface units for all parts of the station into the multiplexer, and then we output a single fiber optic cable from this multiplexer that encompasses or gathers all the information from the station. This way, it becomes possible to use or transmit one fiber optic cable for the entire station or for all the information from the station at once, instead of using separate fiber optic cables for each individual signal. We transmit this fiber optic, which is of the single mode type, through the OBGW located at the top of the tower. Users can access the digital communication network, or what might be called the transmission network, by using a multiplexer that operates with a standard interface, either through the G703 protocol or X21. Use either the 3D or the 4D protocol, or V35. When the fiber optic reaches the other end, we feed it into a demultiplexer, which performs the reverse operation, meaning single input, multiple output. This means we input a single fiber optic and output an Ethernet cable. Then we take one of these Ethernet cables coming out of the multiplexer and feed it into the communication interface unit to convert the signal from electrical to optical. In other words, we input into the interface unit. The interface unit is used to convert the signal from electrical to optical. This means we enter the interface unit, electrical, or we output a fiber optic cable from them, and this fiber optic cable is connected to the relay. This means that whatever we do at the transmitter, we do the opposite at the receiver. In other words, if we perform modulation on the first end, we perform demodulation on the second end. If we encode on the first end, we decode on the second end. If we multiplex on the first end, we demultiplex on the second end. Note with me that the communication interface unit device itself converts from TX as optical to electrical, and at the same time converts from electrical to optical, meaning that the information on the same device is arranged and returned through the same device and the same connections. Ethernet cables that transmit information in only one direction are called half duplex, while those that transmit information in both directions are called full duplex. Full duplex can be achieved by having two pairs of wires to allow information to travel back and forth simultaneously. For those who want to dive deeper into this topic, they should read this standard published in 2002. This section discusses the optical interface that exists between relays and multiplexers. In certain stations, two separate communication channels are used. each utilizing a distinct method of effectively transmitting information, which thereby provides a level of redundancy in the overall communication network. The term redundancy is often misunderstood. It does not simply mean a backup system where one channel can be used independently of the other. What is meant by redundancy is that they operate simultaneously. If one fails, the other will perform its function perfectly. In older stations, two methods were used. But in modern stations, two methods are used in addition to fiber optic communication, in addition to the interfaces, direct fiber optic, channel 1 main 1, channel 2 main DO, interface unit, channel 2 main 1, channel 1 main DO. Similarly, for fiber optic communication, we use channel 2 main 1 for communication through the interface unit. As for the communication method for main 2, it's the opposite. This means that channel 1 main 2 uses communication through the interface unit, while channel 2 main 2 uses direct fiber optic communication. This indicates that direct fiber optic communication is used in channel 1 main 1 and is also used in channel 2 main 2, as shown in this image. This means that direct fiber optic communication is used in channel 1 main 1 and is also used in channel 2 main 2, as shown in this image. It is used in channel 1 main 1 and is also used in channel 2 main 2. As shown in this picture, we want to highlight that the information in channel 1 is identical to that in channel 2. However, this doesn't mean the relay receives the same data from both simultaneously, as this can cause a conflict, meaning a contradiction or clash. To resolve such conflicts, a reference is needed. If there's disagreement, one should be appointed. We must determine which channel has priority for the relay. The channel with priority is the master channel, while the other is the slave channel. Introducing a new term, communication fail, which for a protection engineer means both channels have failed, regardless of the reason. Therefore, you need to establish a reference to resolve these disputes in case of a conflict. If three are in disagreement, one should be appointed. Thus, we must determine which of these channels has the reference or priority for the relay to take information from. The channel that has priority in providing information to the relay is called the master channel, while the other channel is referred to as the slave channel. Here, we introduce a new term, communication fail. For a protection engineer, communication fail means that both channel 1 and channel 2 have failed, regardless of the reasons for this failure. If a fail occurs on channel 1 or channel 2, it is referred to as a communication alarm. This means that if both communication channels go out of service, it is called a communication fail. However, if only one of the communication channels goes out of service, it is called a communication alarm. Use a yellow non-latching LED. If communication fails, the relay reads only local current, causing a false trip signal. This is false if there's no real fault, or it's for a non-protected unit. Block differential protection during communication fail. Ensure testing shows communication fail blocks differential protection. If a communication failure occurs on the differential relay, leading to a false trip signal. In this case, the communication failure is not a real fault, so tripping the circuit breaker is unnecessary. Block differential protection during a communication failure. Emphasize failure, not alarm. In the case of a communication fail, no need to trip the breaker. So what is the solution for the differential current? The solution is to block differential protection during communication fail. Ensure during testing that communication fail blocks differential. Inject currents to keep differential protection stable. In load current condition, no fault. Remove fiber optic from channel 1 and ensure no trip signal from relay. Communication fail, not alarm. Communication fail, not alarm. Inject currents on both sides to keep the differential protection stable in a load current condition with no fault. Disconnect the fiber optic from channel 1 behind the relay to ensure no trip signal is issued. A communication alarm appears, then reconnect the fiber optic to clear the alarm, confirming communication is healthy. Remove the fiber optic from channel 2 to confirm stability without a trip signal, ensuring the communication alarm reappears. Remove the fiber optic from both channels simultaneously, checking for the differential block on the relay LED. After the block signal, simulate a fault by increasing the differential current, ensuring the relay remains stable without a trip signal due to the communication block. Remove fiber optic from channel 2, ensure stability, alarm reappears. Remove cables from both channels, check relay LED for block, simulate fault by increasing differential current, ensure relay stability. Block signal shows both channels failed, no need for communication alarm. We remove the fiber optic cable from channels 1 and 2, RX or TX, to ensure the differential block appears on the relay LED. Once it appears, we simulate a fault by raising the differential current to ensure the relay remains stable without tripping due to the communication fail block. Removing the fiber optic from channel 1 to 2 and the differential block signal appears. Does the communication alarm show? The differential block on the relay shows both channels fail, so no communication alarm is needed. To prevent the alarm from appearing with logic, use an XOR gate instead of an OR gate in the relay configuration, so the alarm only appears if one channel fails, not both. Here, one might ask, if the fiber optic is removed from channel 1 to channel 2 and the differential block signal appears, will the communication alarm signal show up? The appearance of the differential block on the relay is sufficient evidence that both channels are in a fail state, so there is no need for the communication alarm to appear. But how can I prevent the communication alarm from showing up when it uses the OR gate? Therefore, it is preferable in this case to use an XOR gate instead of an OR gate in the relay configuration, so that the communication alarm signal only appears if one channel fails, not both. It can be simulated through this logic, and you can exit this logic if you set a specific condition. This requires enough IPs on the relay. Ensure the differential protection is stabilized and load current is injected, then deactivated by opening DC breakers, and reactivated. It remains stable without issuing any trip signals. This is for channel 2 communication and requires enough IPs on the relay. We must also ensure during this test that if this differential protection is placed in stable mode and a load current is injected into it, and then it is taken out of service by opening the DC supply breakers and then put back into service, it remains stable and does not issue any separation signal. This is a simulation to ensure that the relay will remain stable and will not issue any false trip signals in case the DC batteries are completely drained. There was an instance where the protection relay issued a signal indicating that there was a communication alarm, which means that one of the channels has a communication issue. The reasons for a communication fail in one of the channels include a mismatch in the communication settings or a mismatch in the physical connection of the fiber optic between all the relays on each side. Notice in this communication status displayed on the HMI screen of the Red 670 that the communication fail issued signal 1, which means that there is a fail. The percentage of transmitted signals is 100%, but the percentage of received signals is 0%. Here is a list of the meanings of the abbreviations displayed on the HMI screen shown in the picture. Each meaning or abbreviation indicates a specific problem or cause. The numbers next to these words are digital numbers. For example, if the number is 1, it means that this problem is currently active, while if it is 0, it means it is not activated. Each relay has a first and second port for transmitting and receiving signals, known as TX and RX. If TX in channel 1 is number 1 in local settings, RX is number 2. The remote relay must be opposite. TX is 2, RX is 1. TX1 in the remote should connect to RX1 and RX2 to TX2. In some relays, TX for channel 1 in the remote is 1, RX is 3. Assume TX in channel 1 is 1, RX is 2. In remote relay, settings are opposite. TX2, RX1. TX1 connects to RX1, RX2 to TX2. In some relays, TX1 is 1, RX is 3, TX is 4, RX is 2. Connect odd with odd, even with even. TX1 connects via fiber optics to RX1, same for TX2. The RX number is 1, which means that the TX whose number is 1 in the remote relay must be connected to the RX whose number is also 1 in the remote relay, and likewise the RX whose number is 2 in the remote relay must be connected to the TX whose number is 2 in the remote relay. In some relays, it is assumed that the TX number of channel 1 in the remote relay is 1, while the RX number of channel 1 in the remote relay is 3. TX for the remote relay is number 4, RX is number 2, meaning odd connects with odd, even with even. TX1 in the local relay connects via fiber optics to RX1 in the remote relay, and TX2 in the remote relay connects to RX2 in the local relay. For channel 2, change the channel numbers in settings to 3 and 4 instead of 1 and 2, as 1 and 2 are used. Use 3 and 4 on the local relay, 4 and 3 on the remote relay. Ensure compatibility in relay communication settings and physical fiber optic connections for each channel on both sides for healthy communication. If settings and connections are correct, but there's a communication fail signal, proceed to step 2. Check the communication board for proper function. And why 4000 on the remote relay? Therefore, there must be compatibility in the relay communication settings for each relay on both sides, in addition to having compatibility in the physical connections of the fiber optics for each channel for each relay on both sides. To ensure healthy communication, If the settings are correct and the connections are correct, but there is still a communication fail signal, we move on to step number 2, which is to ensure that the communication board for the relay is functioning properly. Using the loopback test, connect TX in channel 1 to RX in channel 2 and TX in channel 2 to RX in channel 1. TX emits, RX does not. Adjust settings. For channel 1, set TX1 and RX2. For channel 2, set TX2 and RX1. Reconnect TX in channel 2 with RX in channel 1, identifying TX and RX ports. The TX board emits a laser beam, while the RX board does not. After connecting the loopback, adjust relay settings. Channel 1 to TX1 and RX2, channel 2 to TX2 and RX1. Alternatively, perform a loopback for 2 relays in the same station, 1 local and 1 remote. Ensure both communication boards are checked simultaneously. Activate relay communication settings to on, set to 1 and 2 as master, and for the second relay, set to 2 and 1 as slave. And for RX2, we also go to the relay communication settings for channel 2 for the same relay, and we set TX2 and RX1. Or you can perform a loopback test for 2 relays in the same station, assuming one relay is local and the other is remote. In this case, we ensure that the communication board for both relays is checked at the same time. And let's not forget to make sure that the relay communication setting is activated to on, with the setting being 1 and 2, and it is set as master. For the second relay, we ensure that the relay communication setting is also on, set to 2 and 1, and activated as slave. For direct fiber connections, one relay is master, the other slave. It doesn't matter which. With a switch or multiplexer, all relays are slaves. After a loopback test, if the fail signal disappears and rates hit 100%, the relay board is fine. Then, ensure the fiber cable to the interface unit is intact by sending a laser signal end to end. Use a laser or OTDR to check fiber performance, like speed, length, and decibels. All relays should be in slave mode. After performing the loopback test, if the communication fail signal disappears and both sending and receiving rates are at 100% and the communication fail changes from 1 to 0, this means there is no problem with the relay communication board. After confirming that the relay communication board is in a healthy state and has no issues, we move on to step number 3, which is to ensure that the fiber optic cable coming from the relay and going to the interface unit has no problems. This is done by sending a laser signal from one end and receiving it from the other end, ensuring there are no breaks inside the fiber optic itself. A regular laser device can be used, or an OTDR device can be utilized to measure the actual performance of the fiber optic cable, such as signal speed, cable length, and the value of the decibels or others. If the fiber optic cable is intact, proceed to step 4. Ensure the interface unit functions properly by performing a loopback test. The interface unit converts optical to electrical and vice versa. Assume the input is the fiber optic cable and the output is the Ethernet cable. Perform a loopback on the Ethernet cable by connecting TX with RX. Check if the relay's communication alarm signal disappears. If it does, the interface unit is not the problem. If the signal remains, the issue is with the interface unit. Assume the interface unit connects optical to Ethernet cable. Perform a loopback on the Ethernet cable by connecting TX with RX. Check if the relay's alarm disappears after loopback. If it does, the interface unit is not the problem. If the signal remains, the issue lies with the interface unit. Troubleshoot both sides to find the issue. Perform a loopback on the Ethernet cable to check if the relay's communication alarm signal disappears. If it does, the interface unit is not the issue. If the signal remains, the problem lies with the interface unit. Avoid incorrect loopback connections as they lead to false conclusions. Continue troubleshooting to locate the problem. Sometimes a weak signal causes communication failure. In such cases, install a device to boost the signal between the protection relay communication channel and the fiber optic cable. The interface unit itself is often faulty, making it a weak point in the relay connection. Avoid incorrect loopback connections. Decisions based on falsehood are false. We search to locate the problem. Engineers sometimes find communication fails due to weak signals over long distances. Install a repeater unit if the signal is weak, a small device between the relay channel and fiber cable. The interface unit often causes failures, a weak point in relay connections. 2 lines with 2 relays each total 4 relays. Each relay has 2 channels, direct fiber and interface unit, totaling 4 interface units in both stations. So, we install a device that retransmits the signal on the channels again, called a repeater unit. It is a small device placed between the protection relay communication channel and the fiber optic cable. Often, the cause of the communication fail is found to be the interface unit itself and that it is not functioning correctly, making this converter a weak point in the connections with the protection relays. If I have 2 lines in the station and each line has 2 main protection relays, that means I have 4 protection relays in the station to protect the 2 lines. If each relay has 2 communication channels, one using direct fiber and the other using the interface unit, this means that the number of interface units in the station will be 4, corresponding to 4 interface units in the remote and substation. 4 interfaces are in the in-place station. Due to the numerous issues with the interface in the network, research began on how to eliminate them in modern stations. GE released a device called TN1U, which is a multiplexer that we connect directly to the protection relays without any barriers in between. As for the old Fox 515 device from ABB, we need to connect to it through an interface unit. Recently, ABB added an optic card to this Fox, which includes 4 optical boards, in addition to 1 Ethernet board to eliminate all interface units. If we go back to the advanced line differential protection and look at it from the back, we will notice that there are 4 communication channels. 2 of them are for communication between the bond relays in the local substation and the remote substation. This communication is done through the WAN network, which we explained earlier. PlayStation, and this communication is done through colors, which we explained earlier, Miss. They have a separate card called the LDCM, which stands for Line Data Communication Module. As for the remaining cards shown in this image, this is a summary of its names. The 3rd and 4th communication channels are the Optical Ethernet Module, which has a separate card for communication between the relay and the SCADA or SAS system in the local substation through the LAN network. Floca Space Station via LAN network. Of course, the 3rd and 4th channels cannot be used to communicate between relays, and in exactly the same way, the 1st and 2nd channels cannot be used to communicate between relays and relays. This is enough for today's lecture, in which we explain modern communication methods for transferring control, protection signals between stations, whether for differential protection or distance protection. Stay tuned for the next episode, where we will explain the transformer protection scheme in full, detail according to the standards. See you soon.